Let's have a chat now about buffer solutions, what buffer solutions are and why we and nature uses buffer solutions. A buffer solution is a solution that has either a weak acid and its conjugate base, or a weak base and its conjugate acid in sufficient amounts that when an acid or a base are added to that solution, is able to react with that acid or that base you're adding to compensate the change in pH. So it's a solution that resists changes in pH, that if you added a strong acid in water or a strong base in water, it would change the pH very dramatically. When you add it to a buffer solution, the pH change is smaller because you have a weak acid and its conjugate base, or a weak base and its conjugate acid, which is reacting with the acid or a base you're adding and buffers the change in pH. It's not as dramatic as if you're adding these same compounds to water. And a typical example, our blood has a mixture of, well, many things, but it has a buffer solution of carbonic acid and hydrogen carbonate. Sorry, there should be a minus here, I forgot it. So how do you make a buffer solution? Well, either with a weak acid or a weak base. So let's see, for example, the example of a weak acid. You have a weak acid, for example, acetic acid, and you add roughly the same amount of its conjugate base. And the conjugate base of acetic acid is the ion acetate, and you add it as a salt, sodium acetate. So in solution, you have a mixture of acetic acid, the acetate anion, some hydrogen ions, because the acetic acid will split slightly into hydrogen ions and acetate anions, some extra acetate anions because you have added, so you have a few that come from the acetic acid and quite a lot that will come from the sodium acetate, and some sodium ions, which in this case are there because, for the right, they are not going to play any important part. Is the fact that you have acetate and acetic acid, that's going to be the important part of having your buffer solution. So let's have an idea of what would happen. And let's say, for example, you added sodium hydroxide, strong base. Let's imagine if you add sodium hydroxide in water, then what you're going to get is sodium hydroxide and hydroxyl ions. Sorry, sodium ions and hydroxyl ions. Okay? And this will be a significant change in pH because sodium hydroxide is a strong base, it splits completely, it creates a lot of OHs. But what happens if you have in your solution is not only water, you also have acetic acid, HC2H3O, and the anion acetate. Sorry, so 2 minus. Okay, well, an acid can react with a base. We have generate hydroxyl ions, which are basic anions, and it could react with the acid. So it could react with a part of the acetic acid. So you would generate, sorry, this would be only 1 minus. You would generate water and more C2H3O2 minus. So suddenly your hydroxyl ions are not just in water, they are being consumed by the acetic acid to form water. So instead of having a dramatic effect to the pH, the change in pH is barely noticeable or none at all, depending on how much acetic acid you have, because you will have the acetic acid there reacting with the hydroxyls. What happens if you have a strong acid? So for example, let's say that you dissolve hydrochloric acid, you add it to your solution. Well, it splits into hydrogen ions and chlorine ions. If you had only pure water, those hydrogen ions, they would all be changing the pH. You have a very dramatic effect on the pH, a very high concentration of hydrogen ions. But here you have a substance that, the acetate, that can act as a base and react with your hydrogen ions to produce acetic acid. I put the IH at the end, you could put it at the beginning. So suddenly you might not have any hydrogen ions free, or just a few, depending on how much acetate you have in the solution. So you have, that's why you need a weak acid and its conjugate base, or a weak base and its conjugate acid, because you need a part of the buffer solution that will react when a base is added, and a part of the buffer solution that will react with when the acid is added. So if we try to think how a buffer base of an acid, a weak acid and a conjugate base would look like, it could be something like this. You have the acid, let's say acetic acid, you have the conjugated base, the acetate and ion, you have some hydrogen ions that come from the acid, and you have water. And you also have some sodium ions or potassium ions, whatever counter ion that acetate has. If you add a base to your solution, well, it will not stay in solution. It will go to react with your acid, so they will not be there to change the pH. It will be reacting, and if you remember, it generates just more water. If you add a hydrogen ion, so if you add an acid, something that generates hydrogen ions, well, if it was only water, it would have nothing to react with, so it will contribute to changing the pH. But in this case, it does have something to react with. It can react with the base, the acetate, for example, if you are having acetic acid and acetate, to the conjugate base of your buffer solution, and it does not contribute. It will just create more of this weak acid, and the change in pH will be barely noticeable, not dramatic at all. We have something called the Henderson-Hasselbalch equation. There is an equation derived of the acidity constant of the weak acid, or there's another one for the bases, but it is an example of for a weak acid. Of the weak acid, the acidity constant of the weak acid that allows us to calculate what will be the pH of the buffer solution. So if you mix acetic acid and sodium acetate, what pH would you get, and what pH will be able to stabilize? And it's based on the pKa is minus log. We quite like minus logs in acid-base chemistry of the acidity constant. So it tells you that pH equals the pKa, the minus log of the acidity constant of the acid you are using, plus the log of the basic species divided by the acidic species. So the conjugate base divided by the weak acid. And that tells you what is the right pH. Depending on the acidity constant of your acid, you will have slightly different pH ranges in which that buffer solution is effective. So if you remember, the carbonic acid had an acidity constant of 10 to the minus 7. Acetic acid has an acidity constant of 10 to the minus 5. Different acids, the same for bases, but in this case we're talking about acids. Different acids have different pKa's, so they will have different pH ranges in which they act as what we call, good buffering capacity. The maximum buffering capacity is when the concentration of the base and the acid are the same. So these two are the same. The log of, so that would be the same number, so that would be the log of 1, which is 0, and pH equals pKa. That's what we call maximum buffer capacity. In practice, you can play with the concentration of the basic species and the acid to give you different pHs. Maybe you don't want a pH of 6.5, you want a pH of 6.2 or 6.7 or 7.1, and there isn't a specific acid that gives you that particular pH you're interested. You can play with the concentration of base and acid to give you that pH that you are interested on. The effective pH range for a buffer the buffer, when it's at maximum buffering capacity is when has the same amount of base and acid, and an effective pH range for a buffer is pKa plus or minus 1. So you have a bit of flexibility to generate the pH that you are really interested on by using only a few acids. There are lots of biological buffers. I mean, buffers are widely represented in biological systems because maintaining a constant pH in living organisms is very important. Animals, plants in biological systems do not respond very well to dramatic changes in pH from 1 to 3 to 7 to 8. They all tend to have a good or a series of ranges in which they operate at well, and they are happy to keep there, and that's why nature uses biological buffers to neutralize, for example, if there is a reaction that produces a biochemical reaction that produces hydrogen ions or consumes hydrogen ions, those changes do not impact in the overall pH of the system and ruins the reaction and could be actually harmful to the structure and to the activity of the function. For example, proteins, the structure of proteins will be destroyed with the changes in pH. So it is important to keep stable pH ranges for particular biochemical contexts. The three major buffer systems in our bodies are the carbonic acid bicarbonate buffer system, and that's to regulate the pH of water, the phosphate buffer system, and also the protein buffer system. Here's an example. Here's the example of the blood buffer system, the carbonate bicarbonate. Or hydrogen carbonate buffer system, and is to keep the pH of blood around 7.3, 7.4. A very very high pH, 6.8 or more, a pH lower than 6.6 or higher than 8 result in death. So it's a very stringent pH range in which blood needs to be if we don't want deleterious effects to occur. And there are quite a few buffers in the body. That's not the only one. We have the hydrogen phosphate buffer, pyruvic acid, lactic acid buffer, and in this case the carbonic acid, hydrogen carbonic acid to regulate the pH of blood. So this is all. I hope it was useful. It was a lot to cover, but I hope that these videos have given you a good overview of acids and bases, what they are, what we care about acids and bases, what pH is, what we care about pH, and why we have defined the pH scale, and a little bit about understanding of buffer solutions and how they play a key role in the environmental and biological systems. This is all from me, and thank you for watching.